This conference will now be recorded.
Yeah, go ahead. So thank you, Deanna, for the introduction, and thank you all for being here today. I'm going to talk about some of my work from my postdoc at the Southwest Fisheries Science Center with the CalCOPI program. I'm looking at how oceanographic conditions shape rockfish survival in the California current. And then at the end of this, I'm going to talk about how I plan to translate this work to walleye pollock in the Gulf of Alaska and potentially Bering Sea. I want to acknowledge my co-authors, Noah Ben-Adrak, Garfield Kwan, Jared Santora, Isaac Schroeder, Stephen Bograd, Andrew Thompson. And let's dive in. Okay, so effective ecosystem-based fisheries management relies in part upon our ability to understand how oceanographic conditions influence the number of young fish that survive to recruit to the adult population. And this can be particularly challenging to understand, especially with species that have long pelagic larval and juvenile stages that suffer high mortality. This is true of rockfish, who are characterized by really long lifespans, and are characterized by episodic recruitment, where they occasionally will have these really large recruitment events, but the norm is really low recruitment. So there's a lot of work to try and understand how the oceanographic conditions young fish experience during early life influences their early survival. And there's a lot of work to understand what drives mortality during these vulnerable early life stages. And we've kind of come to consensus that predation due to, or mortality due to predation, starvation, and infection are the main drivers of loss during these vulnerable early life stages. And the critical period that determines year class strength can extend from yolk sac larval stage in some species through the juvenile stage in other species, including walleye pollock. So there's a lot of work to try and understand what improves survival. And there's avenues of research that look at the traits of young fish, as well as the oceanographic conditions they experience during development. And then finally, whether or not the characteristics of their parents influence the quality of larvae produced and their subsequent survival. So when we look at traits of larval fish that improve survival, it's generally thought that being bigger is better because you can escape gate-limited predators. Growing faster improves survival because it allows you to swim faster, better capture food, and avoid predation. And developing more rapidly increases your survival because you spend less time in these high mortality windows. So together, these are traits that are thought to really improve survival during this vulnerable life stage. And concurrently, there's a lot of work looking at how the oceanographic conditions young fish experience during these vulnerable life stages can contribute to their survival. And I was fortunate to be working in the California current system during the Green Heat Wave when our understanding of how oceanographic variability related to pelagic juvenile rockfish abundance completely collapsed. We thought that there was a lot of strong correlations between sea level pressure and pelagic juvenile rockfish abundance, which correlated well with recruitment to the fishery. And then we had this huge pulse of warm water that hit the system, similar to in Alaska, and our relationships completely fell apart. And during this time, Isaac Schroeder and his colleagues looked at how deeper water masses might be related to pelagic juvenile rockfish abundance. And they settled on two main water masses. It's the Pacific subarctic upper water mass, which is highlighted with this blue arrow to the north. And this water mass is characterized by being cold, high in oxygen, low in salinity, and entrains lipid-rich large zooplankton. It's thought that this led to improved feeding conditions for the young life stages of rockfish and led to a really high abundance of pelagic juveniles. In contrast, there is what's termed spicy waters, which are a combination of equatorial Pacific water, eastern North Pacific Central water that are warm, salty, low in oxygen, and entrain small lipid poor zooplankton. And when there's a greater influence of this water mass in the system, it's thought that feeding conditions are poor and fewer fish survive to the juvenile stage. But these authors also thought that potentially It's the conditions that the females experience during gestation that may have set up their larvae for success. So when there's more of this PSUW water in the system, females may have better feeding or lower metabolic costs, and that led to improved quality of their larvae and higher survival. And then finally, there's a lot of work that's looked at traits that adult fish possess that may influence the quality of larvae they produce and their subsequent success. And Stephen Berkeley et al. From 2004 looked at how the age of female black rockfish influenced the amount of lipid provisioning they gave to their young and the effects that had on their survival. So what they showed is that older female rockfish provided higher lipid reserves that translated into faster growth rates of their larvae and increased resistance to starvation. So our goal here was to try and marry those three avenues of research together by looking at one trait of larval fish, and that's their core width, which is a proxy for their size at hatch or extrusion. We want to use that to look for and figure out if core width is a good predictor of larval growth and survival. We expected that larger core widths, which indicate larger size at extrusion, would lead to faster growth rates and higher survival. We also want to look backwards and see if there are oceanographic drivers of maternal investment or larval quality. So we expected that there'd be a negative relationship between the amount of spicy water in the system and core size of these larvae, and we expected positive relationships between the amount of PSUW in the system, as well as distance from port and core size. And distance from port we're using as a proxy for fishing pressure. The further you are from port, more likely there would be older, larger females out there that might produce higher quality larvae. So to test these hypotheses, we took advantage of Cal Coffey's winter ichthyoplankton surveys, and we collected genetically identified rockfish from 1998 to 2013. So we used the 8 most common species and pulled, and when I say we pulled, I mean Noah Ben Hadrat pulled almost 1,500 otoliths out of these larvae and measured their core width, which is indicated in orange here. We also measured the recent growth, which is the last 2 increments, the distance between the last 2 increments, and then enumerated age to figure out how old they were, which we're using as a proxy for survival because mortality is really high during these early life stages. So if you have higher average survival in a given year or higher average age in a given year, we're assuming that indicates higher survival. And then we aligned the oceanographic conditions at the regional, the basic scale regional, and then station and depth specific scale, and used partial least squares regression analysis to look at how growth and age were related to the oceanographic conditions that these larvae experienced. We also included, I don't know if you can see my pointer here, maternal provisioning indicator of their core size. We used the winter oceanographic conditions and looked at North Pacific gyre oscillation, Pacific decadal oscillation, ocean Nemu index at the basin scale. Regionally, we looked at meridional winds and biologically effective upwelling transport index. And then at the station and depth specific scale, we looked at the amount of PSUW in the system and the spiciness of the system. And these were calculated for the upper water column where larvae hang out in winter. We also measured port distance. We wanted to look at how the conditions females experience during fall influence the core size of larvae that they produce. We looked at fall oceanographic conditions at the same basin and regional scales, but at the station and depth specific scale, we use PSUW and spice at the depth range for the adult rockfish for each species. And just to give you a quick idea of what that looks like, here's our different species of rockfish, and the bars indicate their depth range. And then the isopycnal layers are the horizontal lines. And we use the ones that best align with where the fish were hanging out. And before I jump into results, I want to orient you to my figures a little bit. So partial least squares regression analysis is pretty similar to principal component analysis, that it breaks down the variability in our data into 2 components. The first captures the majority of the variability, and it's loaded on the x-axis. And variables that contribute positively to that first component will be in the positive x direction. And variables that contribute negatively will be in the negative x direction. Variables that contribute significantly to the variability of that first component will be highlighted in red, and ones that are not significantly contributing are in blue. And then our variable of interest will be highlighted in orange. Okay, so let's dive into what the growth rate results look like. So here's our 8 species of rockfish. We'll note that Sebastian's Mistinus didn't have very many fish that were older than 3 days old, so we couldn't really get an estimate on their recent growth. For everything else, things look a little messy for the top species, but as you get into the bottom, you'll start to see that core size is overlapping with growth rate and is significantly correlated with that first component. So what we found is that our first component explained 8 to 54% of the variability in recent growth. And for 5 out of 7 species, core size was a significant contributor to that first component, indicating a positive relationship between core width and growth rate. When we looked at age, which is our proxy for survival, these patterns become much more clear as core size is almost overlapping age in all of these species. And we found that our first component explained 15 to almost 60% of the variability in age, and that for all 8 species, core width was a significant contributor to that first component, indicating that when you have a larger core size, you're more likely to survive. And finally, when we looked at the fall oceanographic conditions that females were experiencing during gestation, how that influenced the core size of the larvae they produced, we found that our first component explained 10 to 46% of the variability in core size, and we're a little shocked to see how well our hypotheses matched the data here, where we had a negative correlation between spiciness and core width for 5 out of 8 species, and positive relationships with PSUW and distance for 6 and 7 out of 8 species, respectively. So in conclusion, we found that core size actually does do a really good job of predicting the success of larvae, where larger core sizes lead to increased growth rate and higher survival, and that when there are spicy water masses in the system or increased spiciness of the system, that leads to larger core sizes of larvae. And when there's more PSUW or females are found further from shore, that leads to higher size of cores for their larvae. We wanted to dive a little bit deeper into that to figure out what could be explaining those patterns. So this figure shows the average of the 5 highest years of PSUW across the system on the top, and then the 5 lowest years on the bottom, to give an idea of what the conditions were that females were experiencing in this region during those types of conditions. So what I want to draw your attention to is these cross-shelf gradients in PSUW in this top left figure here. So there's really low PSUW generally near shore, and it increases as we move offshore. Oh, I was here this whole time. In contrast, in the low years, there's really low PSUW near shore, and then that stays pretty low as you move offshore. And this leads to drastically different conditions that females are experiencing during gestation. So when you look at temperature, you see the strong cross-shelf gradient of warm water near shore, and much cooler water offshore. In high PSUW years, there's less of a gradient during these low PSUW years. And similarly, we see low oxygen near shore and an increasing as we move offshore. And there's less of a gradient in these low PSUW years. Finally, when we look at nitrate, we'll see that there's a lot of nitrate near shore and extending out into offshore in these high PSUW years. And there's less of a gradient in these low PSUW years. So this shows that females, especially in these offshore regions, are experiencing colder water and higher oxygenated water. And we think this has important consequences for the larvae that they produce. Specifically, we think that because females are hanging out in this higher PSUW water, which entrains lipid-rich zooplankton, that the food web is more nutritious during these years, and that leads to better feeding of the females so they can better provision their larvae. Also, because oceanographic conditions are colder and there's more oxygen in the system, we think this reduces the metabolic cost of females so they can provide more energy to reproduction and provisioning their larvae. And finally, we think possibly that when there's more oxygen in the system, it increases the vertical habitat available to females. They can find or access improved habitats or improved areas of higher habitat quality that may improve their reproductive success. So what we think we've done here is add a little bit of a piece to this puzzle, figuring out how early mortality affects these life stages of fishes. And when oceanographic conditions influence females, that affects the amount of endogenous nutrition they can provide to their larvae. And that may have downstream effects to their susceptibility to starvation and predation. So some next steps here are trying to figure out what the actual mechanism is between what females experience and the pore size of their larvae and what that translates to in their larvae, and then trying to link that to recruitment. And this is something we struggled with a little bit in Southern California because the sampling of ichthyoplankton occurs in the Southern California bight. A lot of the pelagic juvenile rockfish sampling occurs in Central California, so there's a mismatch between where they're sampling. That makes it challenging to align larval traits to the juvenile traits. And that's one of the things I'm really excited about when I get to translate this work to the Gulf of Alaska with the EcoFoci program. So I'm really excited to link observed and modeled oceanographic data for the Gulf of Alaska to look at how what the adults are experiencing translates to our awesome time series of larval otoliths of walleye pollock in the Gulf of Alaska, and seeing if that will allow us to better understand variability in the abundance of H0 and recruits. And some additional ideas I have are trying to drill down and figure out what those mechanisms are for explaining why pore size might vary from one year to the next. And to do that, I hope to collaborate with MACE to collect eggs from reproductive females in their winter pre-spawning surveys, fertilize them at sea, and to look at a range of ages and sizes of females, and then to compare the pore sizes of the larvae that they produce. And also, I'm really excited about the opportunity to use H0 pollock otoliths, which are the next life stage after the larvae, to look at whether or not their real life history traits align with larval traits, or whether or not selection based on early size, growth rate, or the timing of spawning, which Lauren Rogers has shows is highly sensitive to environmental variability. So with that, I'd like to acknowledge the whole Cal Coffee team, who I couldn't have done any of this without, as well as the NOAA and the crew that go out and collect these samples on Cal Coffee surveys, my funding sources, Emily and Deanna for running this seminar. And if you have any ideas or would like to collaborate, please contact me at will.penny@noaa.gov. And if you have any questions, I would love to answer them. Thank you.
All right. So yeah, just look at the comments while I switch over presentations. We'll keep an eye on the comment section, and we'll see if anyone's got comments online or
Anybody in the room?
in the room.
Yeah, Lisa.
I have a question. Did you look, so you looked at nutrients, did you look at phytoplankton like chlorophyll or any satellite information to kind of do that link between,
Did not.
primary production to
Yeah.
and then zooplankton?
Trying to remember. So there may have been some chlorophyll data from the CTD casts. And we initially looked at our CTD data, and then we decided we want to look specifically PSCW and spices that kind of captures some of that. But it could be cool to go back and try and tease that apart. We'll leave that for another postdoc. Maybe I'll keep that in my back pocket.
Yeah. Most of the questions are about the sound quality, which I think is a little messed up. So we're just going to start projecting, and we're going to be really quiet in the room, so that way we can all hear properly.
Well, if there are no more questions at the moment,
Yeah.
please email me or contact me directly. Thank you all.
So this is, can you hear me? This is Rich Bell online. I have a quick question.
All right. So thank you so much. Well, that was a great presentation. Our next presenter is Al Herman. He is a Seacoast and PMEL affiliate, and he's going to be talking about modeling in the past, present, and future. Thank you so much, Al.
Thanks. Okay, so I'll try to talk loud, since that's been requested here. So Yeah, this will be somewhat of a whirlwind tour of some modeling activities we've been engaged in over the past 30 plus years now. And
Yeah, you should be able to.
how do I do this?
Yeah, try the arrow. There you go.
Right, so past, present, and future, some aspects of our biogeochemical modeling and how it's being applied to fisheries oceanography. So I'll start with some acknowledgements. Right up front, it's been a huge number of people that we've collaborated with over the years. My apologies if your name is not here and you think it should be, but it is a very long list. Many fine colleagues we have collaborated with over the years. So as far as the end users of this work, they include the use of our Bering Sea hindcasts for yearly status reports and field planning. We try to update our hindcasts to the present twice a year and offer them to the public. More on that later. Both the Bering Sea and Gulf of Alaska projections are used for a variety of fisheries modeling, both single and multi-species, full food webs, as with the Atlantis model, projections of essential fish habitat, and management strategy evaluation. But not to be left out at the bottom there, individual-based modeling has been an ongoing activity for a couple of decades now, with individuals both here and elsewhere. So way back in the 1990s, we used a model out of the Rutgers shop called the semi-spectral primitive equation model to model the northern Gulf of Alaska, Shelikof Strait in particular. And Phyllis already had some moorings in place that she was maintaining for multiple years there. We made a great resource for comparing the model and with the observations, the observed currents, and you see that on the right there. Comparison of the two, we got a pretty good match and kept that work going. Ultimately, we expanded into a different array of models and a different array of model forcings. This is a master flowchart put together by colleague Liz Dobbins, who's now at UAF. Way back in the 1990s, early aughts, regarding our use of global models as forcing to multiply nested regional circulation models, in some cases driven by multiply nested atmospheric models as well. Those produce physical variables which then drive biogeochemical models, all of that fused with data wherever we could find it, more and more emerging data from the EcoFOSAC program and remotely sensed assets, and these days including sail drones. And in addition, as noted in the previous graph, we feed that into individual-based models as well as Eulerian biogeochemical models. Here's an example of an early coupling of circulation with NPZ and individual-based models. Some work with Sarah Hinckley and collaborators. And the individual-based approach allowed us to get really detailed on pollock larvae, shown down there in the lower right-hand corner. Actually, nope, I misspoke there. This is not pollock, but rather the zooplankton you're seeing there. So this was just a snapshot of some individual-based model output in the Gulf of Alaska. It's fun to watch movies of this in 2D. It's even more fun to render it in 3 dimensions. If you had simple red-blue 3D glasses, you'd see this popping on the screen at you. We did several presentations that way. That was a lot of fun. Expanding on that work, we branched out into active stereo glasses, which are synchronized with an infrared emitter, and you display on a computer screen or a special silver-backed projection screen No, actually, for this technology, you don't need the silver backed. That's a whole other realm. This technology allowed us to work in color and to easily use it for outreach. Here's a photo from our use of that technology at the Seattle Aquarium to illustrate some points regarding 3D circulation in the Gulf of Alaska and Bering Sea. So over the years, we've used a variety of grids and resolutions to address these issues in the Gulf and the Bering Sea and the Northeast Pacific more generally. One of the main ones has been the one you see outlined in blue there, the Bering 10K model. We've also done a good deal of work with the Gulf of Alaska 3K model, 3-kilometer horizontal resolution. That's what that refers to, 10K, 10-kilometer horizontal resolution. We have plans to refine down to 3-kilometer resolution in the Eastern Bering Sea as well. This is a figure from Kelly Carney over in Building 4. Basic features of some of our present models in the Northeast Pacific and the Gulf. We're using the regional ocean modeling system, and in the one-way nesting scheme, we take boundary conditions for the 3K model from the 10K model. We're down to 42 vertical levels. We have explicit tidal dynamics, which create tidal mixing, very important for many parts of the shelf. We have an input of freshwater runoff and iron contained therein the coast, very important for the Gulf of Alaska. Multiple plankton size classes and biology and chemistry, and other details regarding forcing. A fun way to visualize the output is by showing all the variables at once in a single animation, frame by frame. I'm not actually going to show a movie today, but this is just to show you some of the fine detail you get down at 3-kilometer resolution. And one of the things you have to bear in mind when interpreting this and comparing it with data is that the offshore eddies will never be in exactly the right place. There's a whole lot of chaos in nature. You can never hope to capture it all with a model, even a data assimilating model, which this is not. This model runs freely, driven by the observed atmosphere and the observed large-scale ocean. The regional model itself runs freely. But no matter how much data you assimilate, some of the details will always be wrong. Speaking of data, though, EcoFoci has collected a massive store of data, including tens of thousands of CTDs and model samples over the years. This is a treasure trove of information to compare our model output with for calibration and validation purposes. So not only the CTDs, but also the moorings, which are shown in the large colored dots there, M2 and M8. In particular, you'll see pretty soon in another slide. We've used assets like this to compare climatological model output. So here you're looking at October currents at 40 meters depth from the model shown in black arrows, and climatology of the mooring results, the moored results for that month at 40 meters depth. And some decent matchups there, even in some of the smaller canyons, which was nice to see. We can also use data like Ocean Station Papa to calibrate and validate the bigger Northeast Pacific model. And so this is data at line P, Ocean Station Papa, that is, the end of line P. And you'll notice how things got warmer in 2014 in the data. Down below there, you'll notice a similar warming around 2014 in the model. And you can see, again, things don't match perfectly because they never do. We're off by a degree or so at depth. But that's just life in the modeling world. You're always left with some bias, and you find ways to artfully deal with that in real world applications. Now, moving to the Bering Sea, some of the unique aspects of this, as probably everybody in this room knows, some of the people online maybe not so much. Physically, there is seasonal ice with formation in the north with advection to the south. There is strong tidal mixing, which sets up distinct biophysical regimes in the inner, mid, and outer shelf. There are plankton living in the ice, and there's a strong benthic food chain. So all of those things really need to be included in a decent biogeochemical model of that region. So, fuzzy there, apologize. Something got lost in translation. Well, you get the general idea though. Here's our Bering 10K model domain spanning the entirety of the Bering Sea shelf and basin, and with the inner, middle, and outer shelf shown fuzzily labeled in orange, light green, and darker green. That model that we're running includes ice, a single layer of ice, which is sufficient for the seasonal ice formation. And as with the Gulf of Alaska, explicit tides, very important for setting up the hydrography of the shelf. So using some of those wonderful ecofoci assets here at M2 and M8, a comparison of the observed temperatures, one's shown marked data there at M8 on top and M2 on the bottom with their model equivalent. And you can see a very nice correspondence with warm years versus cold. If you look really carefully, you'll notice a persistent bias that we have grappled with and not yet found a really good solution to over the years. That is, our mixed layer is shallower than it needs to be. And there are various reasons that may be, not time to go into them now, but need to talk about them later. Despite those biases, despite the imperfections, we still do a quite good job of replicating the cold pool that is related to temperatures at the bottom of the Bering Sea shelf in warm versus cold years. Observations shown on top from bottom fall surveys conducted by our colleagues in Building 4, Alaska Fisheries Science Center, and our results extracted from the Bering 10K model on the bottom. Sorry about the fuzziness again here. This is the general structure of a biogeochemical model as it exists now in the Bering 10K model. This is a diagram from Kelly Carney. To see a nicely resolved version, go to her paper from 2020. But the general idea here is multiple nutrients, including from bottom to top, iron, ammonium nitrate, ammonium in the ice, and nitrate in the ice, multiple size classes of phytoplankton shown in green, multiple categories of zooplankton shown in blue, and detrital categories shown in brown. Now, we have recently, within the past year or two, begun publicly serving the hindcast output from the Bering 10K model and also our projections of the future, downscaling results from IPCC models. They're available through a server here at PMEL through OpenDAP service. There's also a live access server attached to that, so you can make interactive plots like this through a web browser or through your phone if you wish to. Oh dear. Yeah, I'm sorry the resolution did not come through here. Too many transfers, I guess, between Google and Windows and Macs. All right. The general idea here, though, in words, is you take CMIP 6 models or CMIP 5 models, and we even started this process back in CMIP 3, feed them through a regional model of the Bering Sea using different emission scenarios and different global models, as many as you can afford. That gives you regional projections of the cold pool, bottom temperatures of zooplankton, any number of indices that are modeled by the regional software. Most significantly, this gives you projections of bottom temperature, which are very important to fish in the Bering Sea. The pollock tend to like a colder regime, which leads to bigger, fatter zooplankton. So there's a parallel with Will's talk. And conversely, warm years tend to be not so good. Not so many big fat zooplankton for the fish to eat. So that's all part of the ACLIMB program with many colleagues in this building and fisheries folks next door. Ways paper summarizing some of our recent work shows the different projections for the 3 global downscaled models under 2 different emission scenarios, low emissions and high. And of course, the higher emission scenario leads to warmer temperatures in the Bering Sea, warmer bottom temperatures as we go into the future. You'll notice there's an offset in any of these models between what they say about the present and what the survey indicates about the present. That's the bias issue alluded to earlier. There are various ways of addressing that when you're using these results for fisheries models. One of the things we noticed with the hindcasting work over the years was certain atmospheric forcings were correlated and coherent at a wide band of frequencies with the oceanic response. This is just showing a strong relationship between air temperature and vertically integrated ocean temperatures on the Bering Sea shelf in a particular polygon on the outer shelf, I believe, in this case. And that, among other things, prompted us to try a multivariate analysis where we look at a wide range of variables from the model, from the regional model output, and a wide range of atmospheric forcing variables to see what things tend to rise and fall together. So again, parallels with sort of stuff that Will was talking about with the principal component sort of analysis, except here we're doing principal components not on the raw variables, but rather the EOFs, the dominant spatial patterns of those variables. So you do EOFs first and then do principal components on the resulting EOFs. And when you do that, you do indeed find multivariate modes, patterns of different things in different months, rising and falling together as you examine this year by year. There's a whole lot listed on the left there. One of the things that emerged from this, and Wei deals with as well in her paper, is a shift in phenology in the future. That as you go into the future, the bloom of phytoplankton happens a bit earlier, and the blooms of things further down the food chain also starts happening a bit earlier. The multivariate EOF analysis not only shows us what things rise and fall together with what spatial pattern, it also provides a means to extrapolate these dynamically downscaled results to a much broader array of global forcings. That is, we can now take dozens of different IPCC models, apply them to this new set of statistical rules, and infer what the regional downscaling model would have obtained had we been able to afford dynamical downscaling for all of those cases. So applying that procedure, you get the set of patterns shown on the right there, the inferred increase in bottom temperature under low emission scenario, SSP 126 on the left, the high emission scenario, SSP 585 on the right. That gives you some indication not only of the overall magnitude, but also the spatial pattern of the expected change. Same thing on the bottom for euphausids, one of those nice fat zooplankton that fish tend to like, and how they are expected to decline under SSP 585 on the outer shelf. Let's see. If you want some of the gory details on that recent work, there's Way's paper and on the left and my paper on the right in deep sea research. And finally, some of the most recent work, we're trying to expand into the realm of machine learning. And sorry, it's cut off a little bit there. But what it basically says is machine learning, LSTM, that is long short-term memory method, is used to replicate the behavior of the downscaling model. So we are using machine learning to relate monthly anomalies of the atmospheric forcing to monthly anomalies of the regional response. And the takeaway from the curves there is the blue is the actual downscaled result from a particular global model. The red is the LSTM replicant of that result trained on an entirely different set of models. So as in machine learning, you train it with one set and then apply it to something completely independent from what it was trained on. And we're actually able to do quite well. So this seems promising, and we're intending to pursue it further. There's some NOAA support that we obtained this year. So to summarize and speak to the future just a bit, we've obtained over the years many useful hindcasts and projections for the Gulf and the Bering Sea. There's always room for improvement. There's always a better model out there that you could be using. The details will always differ from reality, but you can produce plenty that's useful to end users along the way. We have public access available for some of this output, not all of it, but a significant chunk is now on the public servers here at PMEL. And we are in the process of transitioning from our ROMS-based set of models to MOM6 under a new NOAA initiative called Climate Ecosystems and Fisheries, CEFI, which is just now spinning up. It's intended to operationalize some of this work, which has been done through dozens of different soft money projects over the years. We've kept it going. And hopefully, the future will hold hardline NOAA support for this work. And finally, we've done some work lately with nascent use of data assimilation to improve our hindcasts. And that will be it. Thanks.
All right. Let's see. All right. Well, we did great on timing there. Let's see if we have any questions. Let's see. All right, we've got one question for Al. What is the time scale for the changes you show in the SSP 126 and the SSP 585 scenarios?
That was basically comparing this decade versus the end of the century. So that's out to the end of the century versus the present.
Nice, awesome. All right, looks like that's all the questions online. Do we have anything in person? Any questions? I have a question for Will. Will, can you talk a little bit more about spicy water? I think I missed what spicy water was.
So it's a term for these two water masses that tend to come from kind of the equatorial Pacific or the eastern North Pacific water. And they term them spicy because they're warm, salty, and low in oxygen.
Oh, all right, that's
As opposed to minty, which are cool, fresher, and higher in oxygen.
spicy and minty. I like that. I haven't heard that before. Thank you. Any other questions?
Yeah, just add to Will's comment. Usually those water masses have the same density, but their temperature and salinity configuration is different. Even though they do tend to have the same density, but one is fresher, one is saltier. it's temperature salinity compensated changes. Sorry, that might be a little bit more.
No, that's perfect. That's perfect.
Thank you.
Huh?
Well, we don't have any more questions. It looks like we're right on time to wrap it up. Thank you so much for participating. Thank you to our speakers, Will and Al. It was a great chat. And yeah, we'll be here next Wednesday.